A Bode plot is a graph of gain, which is the ratio of V out over V in, as well as a graph of phase shift of V out relative to V in over a band of frequencies. You can create straight line approximations of gain and phase based on poles and zeros of a circuit's transfer function. This is something that was developed by Dr. Hendrik Wade Bode about 100 years ago. As you can see in the graphic on your screen now, which is a Bode plot of a bandpass filter, the magnitude of gain is plotted logarithmically on the vertical axis versus logarithmic frequency on the horizontal axis. But phase is plotted linearly in units of degrees on the vertical axis. In the simple 2-resistor resistive divider circuit that we've been making measurements on in some of the earlier lessons, the gain and phase of this circuit is constant across all frequencies, at least ideally. The transfer function of this circuit is simply R2 divided by R1 plus R2, which is an absolute gain of 0.1 and phase of 0 degrees. The logarithmic gain is 20 times the log of 0.1, which is minus 20 dB. The gain and phase of this resistive divider circuit is fixed because the impedance of the components in this circuit, R1 and R2, are fixed and don't vary as a function of frequency. But if we were making measurements on a circuit that included capacitors and inductors, the impedance of these components would change as a function of frequency, as you may have learned in some of your circuits classes. This means that the gain and phase would also vary as a function of the input frequency. Hi, I'm Johnny Hancock, Product Manager for Keysight's Infinivision X-Series oscilloscopes. In this lesson, we are going to characterize the gain and phase of a bandpass filter that consists of a series inductor, capacitor, and resistor, as you can see on your screen now. The measurement we are going to perform is called a frequency response analysis test, but most engineers simply call it a Bode plot test. I'll start by showing you how to create a Bode plot the old traditional way, using an oscilloscope and a function generator, and then I'll show you a more automated way to perform the test if your oscilloscope has a built-in generator and automatic Bode plot capability. So I've done a little pre-homework with this bandpass filter, the series L, C, and R, and I've determined where the poles and zeros are. There are two poles, one at 3 kilohertz, one at about 800 kilohertz, and there's a zero at 0 hertz. Now 0 hertz is off the graph. So this is plus 20 dB per decade going up to where the pole is, and then it rolls off 20 dB per decade, minus 20 dB per decade, which makes it go flat right at 0 dB. Then it hits the second pole and rolls off another minus 20 dB per decade. So this is the straight line approximation. Now, this is my bandpass filter. I've got channel 1 connected to V in. I've got channel 2 connected to V out across the 50 ohm resistor. And I already have my generator set up to generate a 100 hertz sine wave, 1 volt peak to peak. And we're going to take measurements all the way up to 10 megahertz, 100 hertz, 200 hertz, 500 hertz. We'll skip our way up, take about 15 or 16 measurements, but don't worry, I'm not going to do all of them. And so this is the first measurement at 100 hertz. It measures about, again, 1 volt peak to peak. That's where I set it on V in. V out measures just 0.028 volts. So V out, the green waveform, is much, much smaller in amplitude. It looks the same. And the phase is about 88 degrees. Now, if you take the ratio, that would be an absolute gain of about 0.028, and take the log of that times 20. That's about minus 30 dB, pretty much what I expected here. And the phase 88, I didn't draw the phase here, but the ideal phase is about 90 degrees. So the next step is just increase the frequency. There's 200 hertz. Now I need to rescale channel 2 because it increased in amplitude, rescale the time base, take the measurement, jot it down in my table, V in, V out, jot the phase change to 86, and then maybe at 500 megahertz again, I have to rescale. And then you just step through all the way up to, in this case, I'm doing it up to 10 megahertz, and then plot the points. And I also did some homework last night, and I went ahead and plotted. There's the straight line approximation that Dr. Bode predicted, and the blue line is the actual measurements. So you can see it tracked it pretty closely until it got to about where the poles were, and then it's a little off, and you can see it's taken lots of data. Now you can do it like I did it, where I wrote everything down and used my calculator, or it might be quicker if you plug it into your into a spreadsheet and let that do it for you and do all the plotting. But doing it manually like this, I think you might get a little better understanding. So this was the manual way. This is the way I did it when I was in the university. I believe it's the way most engineering students do it today, but there's an automatic way. We'll do that next. So now let's perform an automatic Bode plot or frequency response analysis test. Now there are dedicated instruments that do this. They typically call them FRAs, which stands for frequency response analysis, or network analyzers. But these type of instruments are not likely to be in your circuits lab in the university. They might be in some of the research labs. Some of the newer entry-level scopes do have this capability. And so let's see how it's done. So I'm going to go into the analysis menu and select, it says frequency response analysis, which simply means Bode plot. And then I can set it up. I can set a start frequency. In this case, I'm going to do 100 hertz, a stop frequency, and an amplitude. Oh, and I didn't mention the built-in generator. It requires the built-in generator, and I moved my BNC cable over from the external generator. And then you can select the number of points. I'm going to use the default, which is 60 different frequencies we'll test. When I did it manually, I think I did 16, and when I did it last night, it took me a good 15-20 minutes. This will do it much quicker. Then we just press Run Analysis. It automatically scales at each test point, both the vertical and horizontal, and it begins plotting. The blue trace here is the gain trace. It started right around minus 30 dB, which is what we expected. The red trace is the phase, which I didn't show you in the manual test. Here you can see it flattened out around 0 dB. So there's scaling on the left part for gain and scaling on the right for phase. So we have plotted both gain and phase on the same exact graph. And then we have markers, dedicated markers for the Bode plot. That's these orange triangles where you can measure, and it reads out down here, what the gain and phase is at any particular frequency. So for instance, right here it says minus 11.4 dB, 73 degrees at 1 kilohertz. Before we wrap it up here, let's talk about Bode. Is it Bode or is it Bode? I've received some comments in the past that said it should be pronounced Bode, a long O, a silent E. So I did a little research on this topic, and I found out his family was originally from the Netherlands. He was Dutch. His mother preferred the Dutch pronunciation, which I've been told is Buddha. But his colleagues at Bell Labs, that included people like Claude Shannon and Harry Nyquist, they called him Bode. My professors called it a Bode plot. I expect your professors probably call it a Bode plot as well. So you can call it a Bode plot or a Buddha plot, but it's not a Bode plot. Unfortunately, many of you will be stuck performing Bode plot measurements using the old traditional manual method unless you have a newer oscilloscope like this one with the built-in capability. Or your professor may require you to do it the old way to help you better understand the fundamentals of this measurement. Automatic Bode plots are something that I innovated for the first time in an oscilloscope a few years ago, but more oscilloscope vendors have been implementing this capability into their newer scopes as well. If you go to the URL on your screen, you can download a lab experiment and tutorial document that I wrote on Bode plots. You can also download this Bode plot poster to hang up in your circuits lab or dorm room. That's it for lesson number 10. In the next couple of lessons, we'll be talking about triggering again. See you in lesson 11. Go, Michigan State Spartans. Go, Michigan Wolverines. Go, Ohio State Buckeyes. Now I've probably offended all 3 of these Big Ten schools.